Yes.
Okay, perfect.
Okay, so we begin at 10. So there is difference between Deutsch the defense and French defense about the time that you can ask some questions. No problem. You can spend 15 minutes as you want to exchange with Julie after the presentation. No problem. Okay.
Mm-hmm.
So
okay.
Don't worry about the time.
Okay. Dans 2 minutes, je peux attendre 2 minutes.
Si tu penses que j'introduis déjà le jury pour
oui, on peut faire ça.
Comme ça. Ouais. Allez, on va commencer. On va pas te faire. On va commencer avec un petit peu d'avance. I switch in English because the defense will be held in English. So welcome to Julie Kessler Defense. I'm present. I'm Ludovic Macaire, a full professor at University of Lille, and I'm very happy to to join this committee. Because I'm the leader of the doctoral school MADIS, organize the doctoral track of Julie. So I will present the committee. So we have 2 reviewers who participate by Zoom. Professor Marius Lindauer, so welcome Marius, who works in Leibniz University in Hanover, in Deutschland. And the second reviewer is Florian Ziel, professor at Duisburg Essen Universität, also in Germany. So welcome to Marius and Florian as they follow the presentation by Zoom, and after they ask some questions. And we are very happy to have for this committee Carola Dauer, who is a research director in CNRS in Sorbonne University. So welcome. And there are the team of supervisors. So Margot Berger, who works here in the EDF company. And there are 2 invited members for the committee. And Claire Monteleoni, who accept to co-supervise you during the PhD, and I thank very much you for this. And the first supervisor is Professor Talby from University of Lille, but unfortunately he has the flu, so he cannot be with us. Okay, it's 10. So you can begin.
I can go? Okay. Thank you. So thank you all for coming to this defense today. My PhD is entitled Automated Deep Learning Algorithms and Software for Energy Sustainability. And it's an industrial PhD funded by Électricité de France, EDF, which is the main electricity producer and supplier in France. So the aim of the thesis was to develop tools in order to automate the design of a specific type of artificial intelligence models, which are deep neural networks, to apply them to the task of renewable and load forecasting. So during this defense, first, I will present the motivation for such a subject. So why do we need load and renewable forecasts? And how did we end up wanting to design automated tools to create deep neural networks to forecast those signals? Then I will present the tools that I developed during my PhD. And finally, the application for what I called energy sustainability, but basically are load and renewable forecasting. So first, the electricity, sorry, I just stopped for a bit. Sorry, online, a lot of people just entered the room. This is why I stopped. Okay, so the starting point is that electricity storage is inefficient and expensive at large scale. And therefore, we need to ensure a strict balance between electricity supply and demand. To do so, the current solution is to first forecast the demand and then adjust the production accordingly. However, we have an increasing share of renewables within the electricity mixes, and such production means are not controllable because their production depends on weather, and therefore we also need now production forecasts. In this thesis, we were interested into short-term electricity time series forecasting. This means we are forecasting a few hours until a few days ahead, and this is done using statistical and machine learning models. But we can do that in with different ways. The first idea we can do is to try to design the electricity time series forecasting task as a pure time series task, which means we can use a model to directly model the time series using the time step as input, or we can try to learn the relationship between past data towards future data using time series model. But the issue with such modelization is that it becomes quickly limited because we often have data stream issues within the operational context, and also because actually these electricity time series, they depend a lot on explanatory variables. They can be, for example, weather data or calendar data for the load. So usually we are feeding the models with past load and also explanatory variables. We can also remove the past data from the input and have a regression model. This is particularly useful when we have a data stream issue and we want to have a performing model. And such forecasts can be improved using the past data and online learning. This setup is actually quite popular among the forecasting teams here at EDF. So the challenge with electricity time series forecasting is that it's halfway between the time series forecasting task and a regression task. Regarding the explanatory variables, for the electricity time series, we have two main types of explanatory variables, the weather data and the calendar data. Just to illustrate this topic, I displayed here, for example, the relation between the national French load consumption towards the French average temperature. You can see that when the temperature is getting very low, the consumption is getting high because we have a lot of heating devices within the household in France. And when the temperature is getting high again, around 30, 35 degrees, the consumption is rising again because of cooling devices. Another types of explanatory variables are, for example, the calendar data, which can be month, the days, the weekdays. Here I displayed the average French load consumption per weekdays, and we can see that we have two different types of days in France. We have in blue the weekdays where the industry is running and the consumption is higher, and in dark we have the weekends where the consumption is lower because the industry is down. Most of the explanatory variables can be fed as tabular data towards the forecasting models, but we are trying to incorporate more and more innovative supports. So for example, image data. So here is the example of sky images for PV nowcasting. We can also use weather grids to incorporate spatial information from the weather data. We also have a PhD here in my group where they are trying to use graph neural networks in order to forecast the consumption of the various regions in France. And we had a PhD a few years ago that was trying to incorporate text data within the forecasting model using, for example, weather reports. So when someone wants to design a forecasting model for an electricity time series, this person must make a lot of choices. So here we have a given time series task and a given forecast horizon. And so the first task will be what kind of explanatory variables do I want to use and what kind of format. Depending on them, we can choose a forecasting model. So it can be a time series model, a regression model, and more specifically a random forest or a neural network, for example. And once we have this model, the model is coming with a lot of parameterization that the forecaster must choose. And so the aim of the thesis was to automate some of these choices. And as this is very broad, because a lot of model can be used for electricity time series forecasting, we restrained ourselves to deep neural networks. A motivation for deep neural networks, for example, is that we can incorporate within the neural networks a lot of different data formats, images, text data. And as this is something we wanted to do, deep neural networks seems to be a good fit. So the task of automating the design of a machine learning model belongs to a research area called automated machine learning, or AutoML. The idea is if you have a data set and a task to perform on this data set, and you have an objective function that will measure the performance of a machine learning model on your data set, AutoML will design an algorithm that will automatically search for the best model on your data set given your objective function, and the output will be the best model. If the only machine learning model that you're trying to optimize are deep neural networks or deep learning model, we are in the scope of automated deep learning. And so a neural network looks a bit like this. It's a computational graph with different layers. They are connected with each other. And so we have two subtasks for automated deep learning. The first thing is to optimize the architecture. So it's how what kind of computation do we perform within the layers? How are the layers connected with each other? And so this first task is called NAS, for neural architecture search. And once we have the architecture, it will come with a set of hyperparameters. And the optimization of such hyperparameters is called HPO, for hyperparameters optimization. For example, if you have a convolution layer within your architecture, you might want to optimize the size of the convolution filter. So when someone wants to build a neural network, the first task will be to find the architecture, so choose an architecture. Once we have that, we can choose the hyperparameters, because usually the hyperparameters depend on the architecture. And finally, when we have the architecture and the hyperparameters, we can build the model and train it in order to optimize the weights. So in my thesis, this was done using gradient descent. I didn't work on that part, which I called model training. What I worked on was the optimization of the architecture and hyperparameters. So a typical workflow to optimize the deep neural networks is to first fix a search space. So the search space should encompass all the architecture and the induced hyperparameters that we want to optimize. And so the idea of automated deep learning will be to find the best neural network within this search space that will minimize a certain objective function on the test set. Usually we are given a certain budget that I called it here T, and for each iteration, we will choose a neural network from the search space. We will train it on the trained data set. We will evaluate its performance on the validation set. And finally, we will output the best neural network that we found so far during the T iteration on the validation set, and we hope it will also be the best one on the test data set. Problem is, training a deep neural network is costly in computational and time resources. So we want to choose the T neural network that we are going to evaluate as smartly as possible. So automated machine learning and automated deep learning are organized around three main components. So here is the formula that we are trying to minimize from automated machine learning. And the first component is the search space. So it's it should contain all the design choices that we aim to optimize. And we need to find a trade-off between having a small search space, which can be easy to optimize, but we might miss some promising solution. But if we make the search space too big, the search will be harder. Finally, within the search space, we need to choose a way to represent the design choices that we aim to optimize, and those representations should be usable by the search algorithm. So the search algorithms, it's the strategy to make the smartest choices for the T iteration that we have. And a way to do that is to leverage past evaluation. So I evaluated a certain number of neural networks, and based on this, I will have a strategy to choose the next one as smartly as possible. Finally, the last component is performance evaluation. So it should identify the best model, but also a model that could be that has good generalization properties, and so that has a good performance on unseen data. So the first task when we want to design an automated deep learning framework for a specific task will be to look at the search space and thus the neural network's representation. So I looked a bit what was existing in the literature. There is a lot of research going on the subject. And I will present here two main strategies that I found to explain their limitations for my subject. So first, we have the cell-based search space. So the idea is inspired from the computer vision models. So usually they are made of repeated patterns of pooling and convolution layers. And we only optimize one small pattern of these types of layer. And then we duplicate this cell among the neural network. And another strategies is the so-called one-shot architectural search. The idea is you have a big network that will represent all the architecture that you are considering for your task, and then you will use a search algorithm to find the optimal subnetwork. So these representations are great for a task where we know the deep neural networks are good. So for example, for computer vision task or for natural language processing task, because we need very big models to perform those tasks. And so usually they come with a limited number of candidate operations that we can perform within the networks. And a few of them are tackling hyperparameters optimization. And I found on my data for electricity time series forecasting tasks that those kind of representation were not performing that well. So now I'm going to the PhD contributions. So the first task that I did was to work on a new way to represent deep neural networks that allow the combination of various candidate operation within the networks, and that allow the optimization of the hyperparameters of such layers. Based on this representation, I developed operators in order to modify the representation. And based on these operators, I developed two algorithms to optimize the representation. All of this was implemented as an open source package called Dragon. And finally, what I call the performance evaluation is the application to load and wind power forecasting. So now I will talk about the tools that I developed for the optimization of deep neural networks. So first, on the neural networks representation, and the first search algorithm that I developed. So this was part of a first paper published in Journal of Machine Learning Research. So the idea is to represent the neural network as a directed acyclic graph. So here on the left, you have a neural network with a single input and a single output. The nodes correspond to the layers, and the edges are the connection between them. And the architecture is encoded using the adjacency matrix. So for example, here you have the one on the first row and the second column because there is a link between the input node and the node L1. And then for the nodes, we have a list of nodes, and each node, so each layer, is made of 3 elements, a combiner that can combine the different incoming vectors, because we can have vectors of different shape coming into the node, and we must use a combiner to create a single array that will be processed by the operation. Then the operation can be any PyTorch layer, and the user can also choose the hyperparameters that the person wants to optimize. And finally, we have the activation function. So this kind of representation can be used to create more or less flexible search spaces. So we can directly use the directed acyclic graph to represent the full network, but we can do something a bit more complicated. So here I display the example of a search space that goes from 2-dimensional data toward 1-dimensional data, for example, for image classification. And so we have a first graph where the candidate operations can process 2-dimensional data. Then we have a flattened layer, and we have a second graph here in blue that can process 1-dimensional data. Once we have the representation, we can select randomly T neural networks from our search space, evaluate them, and then take the best one at the end. But if we want to do something a bit smarter, one thing that I thought about was to develop operators in order to modify the representations to optimize them. The idea is if you have a representation, we perform a slight modifications on it in order to find another representation close to it. And we hope this will be better. So here I represent different search operators. They can be seen as mutation or neighborhood operators. So you can, for example, add a node. So on the left, you have the adjacency matrix, and on the right, you have the list of nodes. So here we add a node at the position 2. You can also delete a node. So here we deleted the node at the position 2 also. And the idea is to make sure that we are not producing any orphan nodes. An orphan node will be a node that has no incoming or outgoing connections, and we don't want to have lost layers within the architecture. We can also modify the outgoing connections or the incoming connections. So in this way, we also need to make sure that we are not producing any orphan nodes. And finally, we can change the node's content. I also developed some search operators directly on the HAPA parameters. So the HAPA parameters can be of several types for neural networks. So we can have integers, for example, the output shape of a linear layer. We can have decimals, which can be the rate of a dropout layer. Or we can have categorical variables, which can be, for example, the type of pooling we are trying to use. And so for the integers and the decimal HAPA parameters, we are choosing the new value within the neighborhood, so a range surrounding the actual one. So for when we are looking at a node, we have the combiner and the activation function, which are HAPA parameters. They are both categorical variables, so the new value will be drawn randomly. And for the operation, we can have various type of HAPA parameters. Another way to modify the operations that I implemented is a crossover. So the idea of a crossover is you have two representations, and you will try to mix them in order to create two new ones. And you hope that you will pass a good gene, so a good part of the representations. And so in the case of directed acyclic graph, the idea was to exchange nodes from the graphs. So we have here our two parent solutions, and we are going to exchange the node 1 from the parent 1 with the node 2 and 3 from the parent 2. Those nodes were randomly selected. So here we identified them in the adjacency matrices. And so the first step is to remove them from the graph and to determine which position they will have in the future graph. So this is done using a small algorithm that will try to keep the same structure from the graph. So if we pick a graph at a node at the beginning of a parent, we will try to insert it at the beginning of the new graph. Once we have the position and the nodes, we can insert the new nodes like this. So we created two offsprings that are a new graph where the nodes 2 and 3 from the parent 2 now belong to the offspring 1, and the node 1 from the parent 1 is now belongs to the offspring 2. I had the chance during my PhD to have access to the supercomputer from EDF, which is called Chronos, and I had access to 20 GPUs. And so I had the possibility to develop distributed search algorithm with 21 processes, and they all follow the same kind of architecture. So first we have a master process, and this master process will select the next configuration to evaluate as long as a worker process is free, and each worker process is associated with a single GPU. And so once the master process selected a configuration, it sends it to the worker, which will evaluate on the GPU the solution. And then once the evaluation is done, the worker process can return the objective function from the configuration. So based on this, I developed the first algorithm. Well, not developed, but I used the first algorithm, which is called the evolutionary algorithm. And so the idea is you have a population at time t where you have different neural networks. They have all been already evaluated, so they got different losses. So here's the best one is the yellow one because it reached a loss of 0.1. And at the time step t, if we have a free process, the master process will select two graphs from the population using what is called the tournament selection, and then evolve them using the mutation and crossover operations, and then send it to the worker process that will train both networks. And if at the time step t+1 we have another process that is free, it will do the same thing. And got two graphs that will be trained and evaluated. And after the training, if one of the or the two solutions are better than the worst one from the population, it will replace it. So here we have we got a new graph that reached a loss of 0.4. It's better than the worst one from the population, which was 1, and so it replaces it. And so we will converge toward better and better populations. So we evaluated our framework on a time series forecasting task. So we used an open source data set containing 27 different time series. And we performed one evaluation for each of those 27 time series. So the search base is quite simple. So we have a directed acyclic graph that I just presented above, where we have different one-dimensional candidate operations. So for example, one-dimensional pooling, one-dimensional convolution, and also recurrent neural networks. And after the graph, we have a linear layer that must transform the output shape of the graph until the right output shape from the time series. The objective function, so we used a mass to assess the performance of the architecture and the hyperparameters that were used. This objective function was given within several papers that I compared myself with. So this is why I used this metric. And for the search algorithm, so I used the evolutionary algorithms that I presented just above with a budget of 8 hours and a population size of 100 graph. So here are example of the neural networks that I found. So you can see for the M4 daily, so on the top time series that is managed to find something very simple for this time series. But the framework is also able to find some more innovative neural networks, such as the one for the Dominic time series on the right of the slide. So we compared ourselves with 15 handcrafted models, which among them, there was some time series model, some statistical model, machine learning or deep learning. And also with 6 AutoML frameworks, all specialized for time series forecasting. And so on 11 out of 27 time series, we managed to beat all of the methods. And on 17 out of 27, we were among the top 3. So one limitation that we found with the evolutionary algorithm that we used is that we were given the same number of resources per configurations. And sometimes we know from the beginning that a configuration is bad and we don't need to keep training the neural network until the end. And so we ended up creating a second algorithm that we called a mutant UCB that use Bandit's algorithm and evolutionary operators in order to enforce this what is called resource allocation. So the idea of resource allocation is to find the right trade-off between doing a small training, so giving a small amount of resources to a wide variety of deep neural networks, and doing an extensive training of a few models. And this is called an exploration-exploitation trade-off, which makes us fall under the umbrella of Bandit's algorithm. And in our case, the goal is to output the best model. So we are in the case of the best arm identification setup. The starting point is what we call a reservoir of K arms. And actually, each arm is associated to a machine learning model. So to introduce a bit of notation, we have for each model K, we associate the value n bar K, which will be the number of resources already allocated to the arm K and the model Fk. Nk will be the number of times the arm has been picked, and n will be the maximum number of resources that is allowed per model. For the resource allocation, it means in our case doing a small training of a neural network. So here we see the value n bar k increasing of 1 after doing a small training. And the rewards for the Bandit's algorithm would be the accuracy, in this case, on the validation set. So now I'm going to present the algorithm mutant UCB. For those of you who knows, it's kind of an extension of the algorithm UCBE. But the idea is you have first an initialization phase where you have all your arms and you will perform a small training on each model. So you will give a first batch of resources to each model, and you will get their accuracy on the validation set. And then for each iteration of the algorithm, you will choose optimistically the next arm to pick as the one having the maximum probable loss. So this is the UCB reward. And then you will sample a random variable. If this random variable is equal to 1, we will give a small amount of resources to the arm, so we will perform a small training on this arm. But if the value is equal to 0, we will use the mutation operators that I presented just above to create a mutant. So we will create a new graph that is a mutant from the arm we picked. And we will train, so give a small amount of resources on this arm and integrated it into the population. So the population in this algorithm is growing. For the probability of giving a number of resources or to create a mutant, we use this value, which is 1 minus the number of times the model has already been trained, so the resources already given to the model, over the maximum number of resources, so a small training allowed per model. Which means that at the beginning, when the model hasn't been trained a lot, it's more likely that we are going to keep training this model. But if the value n bar of it is close to n, we will be more likely to mutate the model. And once those two values are equal, we will just keep mutating the model and not performing any training anymore. So we use this algorithm on 3 image classification datasets. So here you have the example on Cypher 10. And so we compared it with 3 other algorithms. So the evolutionary algorithm that I presented just above. We also have a random search and HAPA-BAND, which is a bandit-based algorithm that leverages also resource allocation. And so on the first image, you have the best model accuracy found so far by the algorithm, depending on the time. And in yellow, you have mutant UCB, and we can see that mutant UCB is converging a lot faster than the other algorithm, and moreover, a lot faster than our evolutionary algorithm. And what I found also interesting is the number of evaluated models per such algorithm, which is the table at the bottom of the slides. So we gave the same budget for every algorithm, but for the random search and the evolutionary algorithm, the training was performed until the end. So there is no resource allocations, and they were performing 10. So they were giving 10 resources per model. And so for HAPA-BAND and mutant UCB, we managed to explore more because we, as we are doing resource allocation, we have the time to evaluate more models. So finally, all of this was implemented into an open source package that I call Dragon for directed acyclic graph optimization. And so this package has everything that I presented just above. So there is a part that presents the search space. So with the neural network architecture representation as directed acyclic graph, as well as the encoding of various types of hyperparameters. Then there are the search operators, so the mutation on the architecture and the hyperparameters and the crossover. And finally, there is the implementation of the 4 search algorithms that I presented just above with their distributed version over several GPUs. So Dragon was developed as a toolbox to create AutoDL packages. It's not directly a no-code package, but we can use it to define a specific search space for a given task and then perform an optimization on this search space. So now I will present how I used Dragon for energy sustainability. So let's go back to our supply-demand balance. So we developed 2 AutoDL packages. So the first one is called Energy Dragon, and it's specialized for load forecasting. And then there is a second one that is called Wind Dragon for wind power forecasting. So Energy Dragon was presented into 2 papers, and I will present it as a broad AutoDL package now. So the idea is to perform a national daily load forecast. So the output of the neural network that we want, or daily load forecast. So we are forecasting arrays with 1 value per time step. So for example, if we are doing hourly forecasting, we will output vectors of 24 values. 48 if we are in the case of half-hourly forecasts. So this is an example of this type of curve that we are forecasting for the French load data. And for the input, we had 2 kinds of inputs, so weather data and calendar data. For the weather data, it comes from the data from 32 weather stations in France. And we have the first part of the neural network that will perform weather features engineering. So both spatially and temporally. And this first The first block, the architecture is fixed and we only optimize the HAPA parameters. Then we have the calendar data, and both type of exploratory variables are fed to a feature selection process, which is also parameterized by a set of HAPA parameters called lambda f. Then we are going to the main part of the deep neural networks, and from this part, we are optimizing both the architecture and the HAPA parameters. So it's parameterized by alpha, the architecture, and lambda of alpha, the HAPA parameters. And finally, we have a non-line learning brick that will take the most recent data to improve the forecast from the model. And this brick is parameterized by a set of HAPA parameters that I call lambda of online learning. So this is the final search base of Energy Dragon. And we evaluated using the French load consumption data. So it's open data from the French TSO called RTE. And the validation period, the test period, was the period from the year 2023 and April 2024, which is quite challenging because we had a sobriety effect on the winter. And this is something we haven't seen a lot during the past few years. And so I compare myself with the open source forecast given by RTE, the French TSO, with an industrial model that is used by the team here at EDF to forecast this signal, which is a generalized additive model, so a GAM. And finally, we have Energy Dragon. And so on this period, we managed to improve the forecast from RTE by 20%, and we improve the performance of the GAM by 8.5%. Finally, the second AutoDL frameworks that we developed is called Wind Dragon. So it's for wind power forecasting, and it's also part of the last paper. And so the idea is to forecast regional wind power data. So in this case, we are not forecasting arrays with a value per time step. We are forecasting the instant value. So the output belongs to R. And the input will be a wind speed map coming from a weather forecasting model, a numerical weather prediction models. And the forecast horizon that we use was between 1 and 7 hours. And so this map is fed first to a regional map extraction block, which is parameterized by a hyperparameters that I called lambda f. And then it goes to the main part of the deep neural network, which is also optimized using the directed acyclic graph that I presented just above. So we have the architecture alpha and the set of HAPA parameters lambda of alpha. So the search space is a bit simpler than for Energy Dragon. We have just the HAPA parameters for the regional map extraction and the architecture, and the induced HAPA parameters from the architecture for the main part of the deep neural network. So actually, our target was the national wind power forecast, and we obtained this value using a bottom-up approach. So we had the several weather map for each region, and then we performed an evaluation to find an optimal model for each of this region. We get the forecast, and we sum them in order to get the national value. For the results, so we also used the French data from the TSO RTE. And so here the data is a bit older. It was on the year 2020. We compare the two search algorithms that I presented during the first part, so mutant UCB and the evolutionary algorithm. And we saw that on this task, on our search space, the mutant UCB was performing better than the evolutionary algorithm. And so Wind Dragon is implemented using mutant UCB. And so here we have a more extended baseline. So we have Wind Dragon with mutant UCB. Then we have the forecast from the French TSO. And then we have a handcrafted model that we developed, which is based on a convolutional neural network. We finally have a XGBoost on the mean wind speeds of the region and the persistence, and a model which is just the persistence. And so on the national level, we managed to improve by 19% the forecast from the best baseline that we have, which is the handcrafted model, so the convolutional neural network. And we improved by 38% the forecast from RTE. And on the regional level, I didn't display the results here, but WinDragon is beating all the other baseline for every regions. So now the conclusion. I'm going back to the formula from automated machine learning. And so we kind of worked on the three main components from AutoML. So first on the search space, so we introduced a new flexible way to represent neural networks that can mix various candidate operations. We performed experiments on various types of data. So we had image data with mutant UCB, time series data from the first paper, and also weather maps and various input data for the load forecast. And we show that the representation that we use within Dragons are multimodal. They can process various kind of data. And on the particularly on the load forecasting task, so for Energy Dragon, we show that we can customize our search space. So we kind of fixed some part of the model that we knew were good for the task at hand, and then we let the framework looking for good architecture on the parts of the network where we didn't know what would be the best solution. Based on this representation, we developed several search operators, to modify this representation. So mutation and neighborhoods, both on the architecture and hyperparameter sides. We also developed a crossover, and we used them on the first search algorithm, which was the evolutionary algorithm, and then we developed a new one, which we call mutant UCB, which leverages Bandit's algorithm and evolution. All of this is implemented into a package called Dragon, which we can see as a toolbox to create AutoDL packages. And based on this, we implemented two packages, Energy Dragon for load forecasting and WinDragon for wind power forecasting. Finally, for the perspectives, so I said at the beginning of the defense that we constrained ourselves on deep neural networks because the subject was very broad, but now we might want to go towards automated machine learning rather than automated deep learning for energy sustainability. So I said that a lot of models can be used for electricity time series forecasting. And among them, there is one which is very popular among the load forecasting community, which is the generalized additive models. So we currently have an internship in my group working on developing a tool using the tool from Dragon to optimize the formula of the generalized additive model that we called DRAGAM. So this is an ongoing work. And then the goal will be to perform model selection using Dragons. So we can imagine, for example, a reservoir for mutant UCB where we have each arm associated with different kind of models. And we could select for a given signal if a GAM will be better than a random forest or, for example, a deep neural networks. And we will also have a PhD in an internship going in the next few months on online automated machine learning. The idea is that the distribution of the data is changing among time, and the model that is performing good now might not be the best one in the future. And we might want to detect changes in the data to automatically find the best model among time. And finally, the last thing is more on the deep neural networks part. So for industrial perspectives, we might need to improve the explainability of the deep neural networks because it's important for the forecasting team at EDF to know why a model produced such a forecast. And so we didn't work on that on the thesis, but it could be a nice perspective for the future. And something a bit more specific to my networks is that I noticed that I had a lot of weights that were set to 0. So I guess some pruning could be a nice idea to simplify the architecture that Dragon is finding. So thank you for your attention. This is all for me. And if you have any questions.
So thank you very much for this very clear and pedagogical presentation. It was dynamic. So now we exchange with you about your work. And please, Professor Linda Ward, do you listen to me? Can you exchange with Julie?
Yeah, sure. Yes, thank you very much. It was an awesome talk, and congratulations to all these amazing things you did already. So maybe starting with some kind of basics. So you used quite a bit of evolutionary algorithms and idea from that community, and you commented very briefly, and you see this on it, why not using Bayesian optimization, which is maybe a bit more common actually in the automate community. Can you elaborate a bit about the advantages of both kind of algorithm optimization approaches?
So between the Bayesian optimization and the evolutionary approach.
Yeah, please.
Yeah, so actually this thesis was following an internship that was focusing on hyperparameters optimization for a given architecture. And the students used various meta-heuristics to optimize the hyperparameters, and among them the Bayesian optimization and the evolutionary approach. And when I started my PhD, I wanted to explore a way to represent the neural networks in a more complex way. And what I found with the Bayesian optimization is that the representation usually are vectors of values. And so when I wanted, as I wanted to use graph representation, it seemed to me that it was a bit more too complicated to use the Bayesian optimization. So I know there are some works to use random forests in order to optimize hierarchical search spaces. I didn't really dig into that because, like in my the way I saw the topic, it made more sense to me, and it seems easier to optimize directly the graph using mutation operators. And what we also tried to do at some point was to use graph embedding in order to then perform a search on the embedded space using Bayesian optimization. So I know a lot of works are done doing that. And the problem with that was the encoding of the operation and the hyperparameters. I didn't manage to find a way to efficiently learn an autoencoder to represent the solutions within the latent space.
I see. Great. Thank you. Maybe a bit connected to that actually, because I was a bit confused on slide 11, I think, where you were saying, okay, we can optimize for hyperparameters and for architectures, and in the end, we have actually to do everything and aiming for a very good performance of the model. What is your view on doing it independently, optimizing the architecture and the hyperparameters, so first the one and then the other, or doing it jointly? What is your view on that?
Yeah, so I did it on the first paper. So I tried to because at the time I was using generation-based evolutionary algorithm. So I had batch of populations, and I was using for several number of generations the mutation only on the architecture and then on the hyperparameters. And I saw that that the results were quite the same actually. At the end, it wasn't improving. Maybe the hierarchical way was converging like lightly faster, but it wasn't clear. And so at the end, I just put everything into the box and ran the optimization. And this is, I guess, on the manuscript. I don't know. In the new version, I added things. I did those experiments.
I see. Perfect. Yes. Then maybe asking also a bit for your mutant UCB. I really like how you're doing these kind of stuff that is saying, okay, sometimes more kind of budget and sometimes more doing these kind of generating offsprings. For the generating of offsprings, I wondered a bit about how much knowledge is actually transferable between models, right? So you could start from scratch training, or you could reuse weights you already used, or using any kind of distillation approaches. How do you see any kind of approaches for going from the parent models to the offsprings and transferring models, knowledge between them?
Yeah, so actually the weights that are not, that the operation that are not deleted by the mutations, the weights are kept. And even if the shape of the input is changed, we don't reset the weights, we pad or crop the weights matrices And so it's also true for the evolutionary algorithm that when we are generating, when we are using the mutation operators and the crossover, the weights are given to the offsprings. From my experience, this is not improving the results, but the convergence is a lot faster using this strategy.
I see. Great. Then I wanted to ask a bit, you did quite some nice ablation studies in your thesis, right? Showing what is the impact of different things. But sometimes you show some kind of only a few of the data sets, actually. We were not running everything again on all data sets, which makes sense, right? But I wanted to ask actually, how have you decided which kind of data sets you're using for the ablation studies? What was the important data set for you and why?
The one that were the faster to run, actually. So for the time series, I had so some data set were taking a lot of time, and so I decided to just choose the faster one in order to run the ablation study because yeah, just launching one optimization for. So at the beginning, it was 40 time series. I removed those who were not included into the autogluon time series papers. So at the end, I had only 27 time series, but at the beginning, having 40 time series to having to run 40 optimizations was a lot of work. So yeah, I just choose the one that were running faster.
I see, I see. Okay, nice. Then maybe talking a bit more on future perspectives. So you used more like RNN architectures with ASTM and so on, right? These days, quite big of hype is on transformer models. How do you see the future of your work? Will you include also transformers in the future, or are you saying that's actually for your application case here not relevant? How do you see that?
I guess for the future work, it will depend on what I'm doing. So a lot of work can be done on the candidate operations. So I included the recurrent neural networks, but also on the first touch space, I guess LSTM and JRU, and also some attention layers. But I guess yeah, it will depend on what I will be working on. And so the candidate operation, I will implement them depending on the needs that I will have in the future, I guess.
Okay, but do you see any kind of potential in using transformers, or is that something you say, okay, it's far too big models, that's not relevant here?
I guess you can use it by trying because the transformer has repeated cells kind of, and so maybe we can try. I guess with Dragon you can go back to a cell-based search space. It's possible to just optimize a cell and then pass it to and they'll duplicate it. And so this is the good point of having such a flexible search space is actually you can use Dragon to represent transformer and represent various types of transformers. So you will just need to have the right candidate operations or directly have a transformer unit as the candidate operation. And then I guess you can have it. But I didn't work on such a big data that transformer would be needed. So I don't know how it will actually perform. So it's true for the transformer, but it's also true for various kind of architectures. I didn't try on like very big data. So as the search space is quite broad, it will need some restriction. And so I guess it will be possible because the tools are quite flexible, but it will need a bit of work to do that, I guess.
I see. Okay, good. And my last one would be, you talked at the very end and you see this about global models, and that reminded me quite a bit actually to think about foundational models, right? Foundational models are these kind of large transformer models where you're training on a lot of data sets and it can do a lot of things, and then you can fine tune it on for your specialized task. How do you see the future of training in these kind of settings where people are using more and more foundational models and don't want to train from scratch all the time?
Yeah, so we are tackling this subject here as well. So I'm not a specialist on foundation models. I guess yeah, it will probably be the future of artificial neural networks. Maybe we will still need some small networks that the one that I'm doing for a specific task, or people that don't have the money for to have their own transformer models, foundation models for a given task. So yeah, I know this will change a lot, and I hope that everybody won't do any like. I hope that everybody will not do foundation model in the future.
I see. Perfect. Thank you very much. Then I would pass on.
Is it true?
So I think now it's on my side, isn't it?
Yeah, we hear.
Um, so I would also then start with some say simple questions. So you concerning the applications later on you showed us in the wind and the load forecasting. Essentially, in both situations you used weather forecasts as an input, and
Yeah.
and to some extent also calendar variables that you mentioned here. Particularly for the load forecasting, what kind of calendar variables did you include into your studies?
So there are a lot of them. So like we did the PhD as I was given some calendar variables from the team here at EDF. So I didn't really work on that part. So it was already given, but it includes the months, some date types like the holidays, the days before the holidays. Also, we have some trend variables, and yeah, a lot of other things, I guess. But yeah.
It's okay. So you have some indicators, for instance, for the holidays, which is kind of common.
Yeah.
Do you think the models that you design are able to tackle structures like also we have them in France, regional public holidays that only occur in some parts of the country? Do you think is it tricky for the models to capture those behavior, or do you think it's no problem?
I don't know. I guess it will be hard because it will be mixed into a lot of other effects. So maybe like if we are doing a bottom-up approach, it will be a bit easier to include them. But in any case, what I did is that I was given like, I don't know, maybe 50 features, including weather and calendar data. And so it seemed essential to do some feature selection. And so the feature selection is done during the training. And we could try to add those variables and see if the model is taking them as input, is selecting them at the end. But yeah, sometimes I noticed that the neural networks were able to were keeping some. Oh, Florian is gone, I guess.
Sorry, I was kicked out for some reason, but it just seemed to be the case for me, isn't it?
I'm just trying to change the screen because people are not seeing you, but I don't know how to do that. I can't do that. Okay, so I will just share back the other screen. Okay, so I was answering on the region holidays. I don't know if you hear me. It's disconnected again. Oh. Yeah, Florian, can you hear?
I can hear you again, and I see you. It's fine.
Okay.
I don't know what happened, so for some reason I was out. Anyway, and I didn't. Yeah, I think I got mainly your answer. I think I'm not sure what. So I asked the question on the regional holidays, but I didn't get your answer.
Yeah. So the first part of my answer was, I guess it will be challenging, and maybe a bottom-up approach will help to include those holidays. But the other thing is that so I was giving a lot of explanatory variables for the models, and so I used feature selection methods in order to select the features that I wanted. And so I guess we could just try to use them and see if the model is actually selecting those variables. Sometimes I noticed that the deep neural networks were finding some informations within the features. And I don't know how it managed to do that, but yeah, any kind of small informations could help, I guess. But yeah, we should try to see.
Okay. Um, so maybe going into the algorithms, also into the learning. If I got it correctly, for improving your models, whenever you select the best candidate sets of models and you create the offsprings and so on, you're only looking for the objective itself.
Yes.
So if I got it correctly, the computation time you required for the corresponding graphs were not taken into account. So it could be that you have, say, really well-performing models into your bag, which, say, take a lot of computation time, but maybe they are slightly worse ones, which are, but much faster, say, in
Yeah.
training because they are smaller and have a simpler design.
Yes.
How could you modify the algorithm to take also into the account the computation time? So that's maybe worth trying, say, thousands of small fast models to find a better architecture instead of maybe just a few very heavy ones. But I think you know what I mean.
Yeah. So we can actually when we are using Dragon, the training and the objective function are left to the user. So a thing that can be done is within the loss function to the objective function to include the training time. And in this way, we can penalize the algorithm that take a lot of time to be trained. And another thing is that as we are in a distributed fashion designed for the search algorithms, actually the models that train faster have a kind of an advantage because they go back quickly and can be called again. As the models that take a lot of time to be trained, they are stuck within the the GPU they are trained on, and so they can't be attributed any more resources, for example.
Okay, I think I got it. Yeah, yeah, it's true and it makes sense. But maybe for understanding, so did I got it correctly? If you said the model is stuck into the GPU, but still, of course, the GPU trains only new offsprings, which are mutants to some extent, or of the old models. So it could be that some GPUs or essentially at the end, maybe all GPUs train very related, complicated models.
Yeah.
So this can happen. Okay. Yeah.
Yeah, for mutant UCB, we don't train it we don't train only the offspring. As we attribute some resources, we also train all retrain all models, so it can happen.
Okay. So and then one thing is I think you expected this is the objective. The objective that you took for all your algorithms. So if I got it correctly, your main objective was to minimize the MAPE.
For load, yes.
Yeah.
For load forecasting task.
Yeah. For the load, yeah, I just have the load in mind. You wanted to predict the MAPE,
Yeah.
to minimize the MAPE, which is completely okay if this is the objective. But when when training the submodels, for instance, looking for, yeah, you had this flowchart, the other designs. I think if I got it correctly, you minimize the MSE.
The MSC is to optimize the weights. So just for the training part, actually.
Yeah, just for the training part. But why you're optimizing the weights with respect to the MSE and not with respect to the MAPE directly, because the MAPE is the thing you want to optimize at the end.
Yeah, because it seemed to me that it was a lot easier to use the MSC, which is broadly used for to train deep neural networks. So this is what I used the MSC. I don't know how the MAPE will work to train the weights with the gradient descent and everything. So I didn't try it, but I guess if we could manage to optimize the map also for the weights, we could get better results, I guess. I don't know how the landscape of the map will be, and if it will be easy to perform the optimization of the weights on that.
Okay, so well, MAPE is essentially a mean absolute error and then some percentages on it. But do you know the different properties of the MAE and MSE?
Well, the MSE is differential everywhere, and the map is not differential on 0. I guess it's an absolute error, and
Yeah.
then yeah.
So this is from the shape itself. So this is true, but the result, the objective. So what are you minimizing? Do you know the differences? So.
No, I don't.
So maybe I want to point out something which is related to essentially probability theory. So if you minimize the MSE, like in a simple linear regression, so what you estimate is the expected value of the underlying random variable.
Yeah.
Yeah. Do you know what happens if you minimize the MAE?
Well, you will minimize the absolute, so the median of your.
Yeah, but what characteristic will you get if you minimize the MAE?
You will penalize less the extreme values.
Yeah, this is true. So it's not a problem. So, but it's the underlying thing which you minimize is the median.
Yeah.
So this means you're training then against the median and not against the mean. And
yes, this is what I said. Yeah.
yeah,
We agree on that.
yeah. But or the 50% quantile. But however, do you think for your type of data, so even if you just say you train something on the MSE and then later on evaluate on the MAE, do you think it's a problem? Is it in your data? Is it?
Yeah, I guess you're not minimizing the same thing, and so I guess you will be better if you minimize maybe the median on both approaches. Well, yeah, I guess you might be better, yes, but
So
yeah.
Yeah, so my feelings, as I say it, is that if you would just minimize on MSE but evaluate on MAE or MAPE, for the wind data, the differences will be much bigger than for the load data. Do you know why?
No. No.
Okay, it's so. Do you know when mean and median are the same?
When mean and median,
Yeah.
when you have the same number of value for
Yeah.
on each side of the mean.
Well, for instance, so the standard thing is so if random variables are symmetric, you know,
Okay.
so if they are symmetric, we tend to have mean and median are the same. And if you look at the load data and the histograms of how they look like, they are quite symmetric. So actually for load, it doesn't really matter if you minimize MSE and MAE. And then, of course, it makes sense to use MSE because the optimization is faster. Because you mentioned you're smooth and the gradients are nicer and so on.
Yeah.
But for wind, the typical wind shape is a bit more like Weibull type-ish and skewed, and there the differences are much, much higher. Yeah.
Okay.
But just as a kind of side note. Um, okay. For your experiments, you showed also, of course, you compared against some benchmarks.
Yeah.
The benchmarks, of course, were much simpler in their structure, and the computation time is also much simpler. Also much lower than your extremely, I don't know how many GPUs in computation power is behind your Dragon. Do you think if you would say invest those times in, for instance, just improving a GAM and trying different features and so on with the same computation time, do you think the result will be the same compared to your Dragon?
For load forecast, so for the baseline for load forecasts, the GAMs that were given were like the results of maybe years of experience from research engineers. So I don't know how compared to that, Dragon is quite fast, I guess, to find a good solution. But we are actually trying to optimize the GAMs in the same way that we are optimizing deep neural networks. And yeah, the training is a lot faster. And yeah, maybe in 1 or 2 months, I will be able to answer this question. Yeah. But yeah, it should be noted that it seems like a lot of training and a lot of computational time, but actually what we are replacing is not the training of a single model. It's the engineering of a model, which takes a lot of human resources and also computational resources that the people are actually trying different configurations.
So if I got it correctly, so you're working currently at this gum dragon thing, say like this.
Yeah, it's an ongoing work.
The resulting models, will they preserve interpretability of the gums?
We are trying to enforce that, yes, to prevent from duplicated features within the different factors of the GAM, and yes, we are trying to keep it as close as the handcrafted GAMs used by the team here.
Okay, so essentially it's in hyperparameter search and a model search for GAM models.
Yeah, what kind of splines do you want? What kind of features for each spline, and yeah, the factors of the spline, etc.
Yeah, got it. Okay, thanks. So yeah, from my side, that's sufficient.
Thank you, Florent. So now I give the talk to Carola Doer.
Thank you very much, Ludovic. Thank you very much, Julie, for the nice presentation. Very impressive work, very relevant work. And I think it's also, AutoML, I always see it as a topic that is unfortunately a little bit underdeveloped in France. I think we have a lot of machine learning going on, especially in Paris. AutoML is a topic that is not yet that well represented. So very happy to see this work. And also in collaboration with EDF to see that this is really, it's not just toying around with some image classification, artificial image classification tools, but it is actually very relevant work that will have impact. Because as we all know, indeed, we are facing a whole phase transition in how we will produce and use energy. And this may be a first question. So everything you do is very centralized, right? You gather all the data and then you have your model, you run it in a centralized fashion. When I think about usage of energy, we could think about smart products, right? That use energy depending on how much supply there is. And then you switch on whatever the fridge goes on and when there is more energy available and so on. Do you think that, like, have you ever thought about your models in a distributed fashion? Do you think there's a possibility to have smaller forecasting models and deploy them?
What do you mean by decentralized? Like to have different models that were given different type of data, like in a
for example, I mean,
like
I understand that you look at a very,
or...
very highly aggregated level, right?
Yeah.
But do you think that you could like de-aggregate it and have similar successes and similar, I mean, would any of these be applicable to much smaller scale models that could potentially run in my fridge or in my washing machine and then switch on my washing machine when there's a lot of energy being produced?
Yeah, so this kind of data are way more challenging to forecast than the aggregated level. So I guess we had an internship like on global models to forecast 2,300 time series. So it's at a much more local level. So the results are not, we didn't like, it's, I couldn't say anything about to be sure of. I guess we need to work more on that, but there is a perspective to use Dragon at a much more small aggregation level. I guess the challenge is that maybe we need to think about the candidate operations that we are using within the graph. They were very well adapted for national forecast. So we worked on this during the first year of the PhD, what kind of candidate operations could be pertinent for this data. And I guess at the smaller level, you don't have, you still have the influence from the explanatory variables, but also from much more from past data, because the people have very shapes that depends a lot from past data than maybe from the explanatory variables. So yeah, I guess if we worked more on the candidate operation and the learning setting, then once you have, let's say, a pertinent neural networks to perform this task, you can just run Dragon and it will find a better one, I guess. I hope.
Okay, thank you. And I mean, speaking, you already mentioned the operators and that you invest. I mean, you develop your own essentially mutation and crossover operators. You had these repair mechanisms to make sure you don't have orphans and so on. Did you ever check which of the operators are the most relevant for the quality of your results?
We try to do that a bit for mutant UCB because we want to include some interpretability. So we try to use several models with different losses and run different mutations to see if we have kind of relationship with the initial model, the mutation, and the performance of the mutant. We didn't find anything, so this will require a bit of further work, I guess. But yes, this is something that we really tried, and it's really hard to know what was actually relevant. So we know it's relevant because Hyperbrand, for example, doesn't perform as well as a mutant UCB, which includes the mutation. And we saw that the best performing model were always the mutant, but it's not clear what part of the algorithm actually works. And it's very frustrating for me to develop this and don't know why actually it works. So it works. And yeah, we try to run more experiments to try to understand, but yeah, nothing was very conclusive, I guess.
Okay, sounds like a bit like black art, and sounds like at least you're not automating your own job of designing these operators, which may be good news. Okay, another question I had is like you make a strong emphasis on this resource allocation problem, and this reminds me a lot of multi-fidelity optimization. Do you see parallels, or I mean, is it the same, or are there differences? Did you check literature on multi-fidelity optimization? Did you get any inspiration from that, or?
Yeah, not really. Like, I know this is very similar. I heard the name multi-fidelity reading papers or at conferences. People were saying when I presented the first algorithm, oh, you should use multi-fidelity. And so for me, multi-fidelity was quite similar than this, but I didn't look more deeply into that now.
Okay, good. I mean, essentially, you only have different layers of like how much time you invest into evaluating, and then you try to. It's very similar to resource allocation.
Okay.
Fact. Yeah. Okay. Then another question. So you mentioned this evolutionary algorithm, and you said, and then we use population size 100.
Yeah.
How did you choose 100? Why did you ever question, or?
So at the beginning it was 40 because I had 20 GPUs. And then I developed the steady state, so asynchronous version. And I was like, maybe I can have bigger populations, but I didn't dig into the fitting of such hyperparameters. So it was taking a lot of time to choose them. So we tried a bit to compare the different algorithms. So we set, for example, the population of mutant UCB to be a bit more bigger at the beginning than the one from the evolutionary algorithm, as we are doing like smaller training at the beginning. So we tried a bit to fix that, but it will of course require more work on this part to fix the hyperparameters. But I guess maybe it's something that it's also data dependent. So it will also depend on so the hardware you have, and also how much time does it take to train on deep neural networks. So if it takes a lot of time, then your population would have to be smaller because you have time constraints. And on the contrary, if you have more time, you should have you can have bigger populations. For me, like fitting a 100 was quite good regarding the data. So I spent maybe like the first 5 hours training this population, and then I have enough time because I had a time constraint on how longer I could use the GPUs. So I didn't want to spend like 70 hours running the initial population. And also, if the population was too small, the algorithm was converging too fast also. So it was kind of engineering since 3 years, and I ended up with 100, but could be changed.
Yeah, okay, no. I mean, it's a question how relevant it is as well. And I think we cannot automate all the parameters. I think that's my point, right? Is that, because you're just adding layers and layers and layers, and then you have to stop at some point.
Yeah.
I think that's, so I think my point is that even if we talk about AutoML, there are still certain design choices, as we have seen with your operators, as we see now with the population size, as we could probably, I could point out a few more where there will still be like manual choices to be made, and we would still require an expertise of people like you and your colleagues to choose and the right models and the parameters.
Yeah, definitely. AutoML of AutoML. Yeah.
Yes. And okay, so then maybe one last question was about the. So you mentioned that you have different for the Wind Dragon results. You develop different models for the different regions. So
Yeah.
you have a model for Bretagne, for Grand Est, and whatever.
Yeah.
And did you ever check these resulting models? Are they very different, or are there similarities? Is there if like regions that are close by have similar models, or is it complete chaos? Or
So actually, what I didn't mention during the presentation is that I run only one optimization for all the regions. So actually, when a norm is picked from the reservoir with mutant UCB, we attribute a region randomly, and then the loss will be the loss on this region divided by the loss of a reference model, so it can be comparable. The idea was that the architecture and hyperparameters could be quite similar with the region, as we are learning quite the same problem. It's the weather maps, and we forecast the production. It was also a lot faster to do rather than having one model per region. But during the optimization, once we found an optimal model for a given region, we save it. And so the model can be different at the end. And actually, they are very similar because we did this we did this optimization with the whole model, all of the models at the same time.
I see. Okay. Interesting. Okay.
Yeah, but they have small differences with hyperparameters, but generally the models are very, very similar.
Okay. Interesting. Thank you very much. Yeah.
Thank you.
I think that's all from me. Thanks.
Thank you, Carola. I changed my role and ask an exchange with you before before I give you the talk. Okay. So I'm not a specialist about your domain because I work in image analysis and hyperspectral image analysis. So sorry, I have some question about as a beginner student. But as a beginner student, I was I want to congratulate you because okay, your manuscript and your thesis is very well written. It's very clear, the notations are clear and so on. So it's a pleasure to read it. And I'm sure that a lot of PhD or master student will read it. It's a reference, I think. So congratulations, because it's not easy.
Thank
you perform an academic and okay, company and industrial thesis. So it's not so easy. And congratulations for that. I have some questions about we speak about the initial value, the number of populations, but also it is, if I'm true, it is a hierarchical research. So at the beginning, you find the best architecture, and after you fine tuning for the hyper parameter.
It's how I presented it, because
Yeah.
in the theory it's like this, but in the practical implementation, I tried to do the architecture, then hyperparameters, and it wasn't improving the results. So actually, when I'm running the mutations, for example, I can modify only the hyperparameters or the whole operation or the architecture, and actually everything is optimized at the same time.
Okay, but how do you choose to switch between optimization of architecture and optimization of the hyperparameters? How
It's
do you
random.
change?
It's random.
Ah, it's random. Okay.
Everything is random.
And
I try to enforce some rules, but
okay,
random is
okay.
performing better.
Yeah, but at the beginning, in the initial step, the hyperparameters are set.
Randomly chosen.
Oh, okay.
Yeah.
Okay. And we say that okay, it is like the behavior is like a black box.
Yes.
But do you see how evolute, how change the best model at each iteration to serve, because you show us as the best at the end of the but during the research how it evolute. It is a strong evolution, the model changed strongly, or only some kind of hyperparameters, how it change? Do you study the evolution?
I enforce at the beginning of the research to have a small number of layers. So usually it's like less than 4, like 3-4 layers, because I wanted to start with like a simple population and then converge toward better ones. And so, yeah, the changes are actually quite large, because at the end we have, like for some experiments, we had very big models at the end. And also what I did for some experimentation is to include models that I knew were good within the initial population. And the results are actually quite different from the inputs. But I didn't look at every of the hundreds randomly initialized population, but at the convergence is very strong. Like I guess we are changing the model during the optimization.
Okay, thank you. And you have an intuition about the mutation, and you're right. Okay, when there is between the mutant and original model, there was a similar accuracy.
Yeah,
okay.
We try to look at it. And
but are you true of that? Is it always the case? Because when there are only a small mutation, it can provide a different accuracy, no?
Yeah, so yeah, we try to look at it and try to see if like the mutant we're having an accuracy that was close to the original one. And no, you're right, it's not the case. And usually the distribution of the mutants is very close to the one from the random initialized population. For some individuals, we saw that actually it was a Gaussian, maybe higher or a bit lower than the original model, but we couldn't conclude to any like conclusion on how the mutation is actually transforming the accuracy of the models. No, we didn't find any rules or any intuition. So we know that for some model, a small mutation is able to increase the performance, but we didn't manage to find what kind of model and what kind of mutation is doing that. We know it's true, but yeah, I couldn't find any rules on that.
Okay, thank you. So thank you very much for this exchange, and congratulations for this presentation.
Thank you.
So thank you, Julie, for this very pedagogical overview of your work. So I won't ask any question, but I'm going to share a few anecdotes. I'm sorry for some of the jury, but in a moment I will switch to French in order to better express my feelings. So I wasn't there at the start of this wonderful adventure that is a PhD. Your research area was a bit far from my subject, and coding with Torch seems crazy to me. So we first talked more about feminism and ecology than math or mathematics. And then while jogging, we discussed about AutoML and genetic algorithm. As I struggled to keep up with you, a little out of breath, I said to you that testing a bandit approach together would be really fun. You exposed me the huge work you did during your first year, and we started working together. So I reviewed your first article and crossed it out a lot. Sorry again. After hours on the blackboard, many failed the experiment on Kronos. Mutant UCB was born, and unbelievably, it is very strong. You and Etienne have done some remarkable work on wind forecasting. With Eva, you won the data challenge on flood prediction. You took part in many conferences, initiate several collaborations with EDF and INRIA Paris. PhDs have generally nothing to offer but blood, toil, tears, and sweat. It was particularly true of yours. I won't go into the details, but you have shown incredible resilience. Congratulations on all your scientific work. I'm convinced that the tools you have developed will be widely used at EDF and elsewhere. So, long live Dragon. Je vais rapidement résumer ce que je viens de dire pour les proches de Julie et passer à 2-3 anecdotes plus personnelles. Donc, j'étais pas dans l'encadrement du début de ta thèse, et c'est après un jogging sur le plateau de Saclay assez musclé, lors duquel on a discuté AutoML et Bandit, que nos sujets de recherche se sont croisés et qu'on a peu à peu de plus en plus travaillé ensemble. Ce n'était pas toujours simple, mais tu as fait preuve d'une grande persévérance. La qualité de ton manuscrit atteste de la pertinence de tes travaux, tant sur le plan de l'apprentissage automatique que sur le plan métier, c'est-à-dire la prévision de séries temporelles nécessaires au bon fonctionnement d'un réseau électrique bas carbone. Ta rigueur scientifique, ta créativité algorithmique, ainsi que ta capacité à communiquer et à vulgariser ton travail n'ont eu de cesse de m'impressionner. J'étais ravie de partir en conférence avec toi. Ta première présentation au JDS, donc les journées des statistiques, était un vrai succès. La bière belge lui a d'ailleurs fait honneur. Ensuite, on est parti en train à Vienne, puis à Bordeaux, et puis tu as volé de tes propres ailes et j'ai eu de plus en plus de mal à suivre ta cadence effrénée. Quoi qu'il en soit, c'est toujours un plaisir de travailler avec toi, que ce soit pour tester des idées parfois un peu folles, écrire des papiers, encadrer des stagiaires, trouver des noms farfelus aux algorithmes. Ces 3 années de thèse ont, il me semble, été riches en émotions et en apprentissage. Tu connais la valeur de ton travail et tu fais preuve d'une grande maturité. Bref, une fois n'est pas coutume, pour utiliser une expression de fouteuse, je te trouve très solide sur tes appuis. Je n'ai aucun doute sur le fait qu'une grande carrière dans la recherche, qu'elle soit privée ou publique, s'ouvre à toi. Et j'espère de tout cœur que nous aurons l'occasion de multiples collaborations. Pour finir sur une note un peu plus politique, dans quelques minutes, la communauté des docteurs en apprentissage automatique sera, a priori, rejointe par une brillante femme écolo. Je m'en réjouis. Bravo, Julie.
I also prepared my remarks in French so that Julie's friends and family could understand. Sorry to the German jury, but maybe you'll understand because I have a strong American accent. Quand j'ai rencontré Julie pour la première fois en 2023, elle était dans le début de sa 2e année de sa doctorat. Ça veut dire qu'elle en était même pas à la moitié de la durée de son doctorat. Pourtant, elle avait déjà fait une œuvre et des applications d'une qualité et quantité d'une thèse doctorale. Alors, c'était une évidence, ou en anglais, un no-brainer, pour moi de l'inviter dans mon équipe de recherche. Dès son arrivée chez nous, elle a donné un exemple exceptionnel à tous mes nouveaux étudiants et je la considère comme une membre fondatrice de notre nouvelle équipe projet ARCHES, AI Research for Climate Change and Environmental Sustainability. Ça m'a alors fait beaucoup de plaisir de rejoindre ses encadrants et même de la recruter pour un postdoctorat. Du coup, maintenant, nous préparons notre premier travail ensemble. Julie, merci de nous trouver et de nous avoir enrichis avec toute votre créativité, énergie et joie de vivre. Toutes mes félicitations pour cet accomplissement.
Thank you.
Thanks. So I think it's the end. We propose to exchange in another room and we go back. So Florian, Marius, we change. So we spend the 5 minutes to go to the other room and we change the link to no. Yeah. It is it is another Zoom link. It is I think in the second one.
Yeah, the second
to
one from
exchange,
the email.
Bien après, oui, je crois que ils vont venir après. Ouais. Ouais. Bon, c'est le grand moment. Bon, d'abord, on est tous impressionnés par le public. Vous êtes nombreux, c'est pas souvent. Donc, bravo à vous d'être restés. Merci pour votre patience. Alors, déjà, durant votre soutenance, qui a été très pédagogique, vous avez présenté vos travaux sur l'optimisation de modèles deep learning appliqués à un système électrique durable. Ça, vous le saviez, avec des transparents qui étaient très clairs. Ces travaux sont innovants et ils combinent des contributions académiques et industrielles sur la prévision de séries temporelles appliquées à la gestion de systèmes électriques. Ces travaux se situent à l'interface de l'apprentissage, de l'optimisation et du développement logiciel, ce qui n'est pas courant. Tous les membres du jury ont trouvé que votre manuscrit était remarquable, remarquablement écrit, et ça ne fait aucun doute qu'il fera référence dans votre domaine. Vous avez notamment ce manuscrit présente aussi un outil open source, c'est pas si courant que ça, qui est bien documenté, alors qui s'appelle Dragon. Vous nous expliquerez d'où vient l'origine de ce nom, et qui est manifestement déjà exploité ici par vos collègues à EDF. Donc ça, c'est une très très bonne chose. Vous avez répondu à de nombreuses questions, et ces échanges fructueux ont montré votre grande maîtrise sur votre sujet de thèse. Et enfin, vous avez profité de cette présentation et de ces échanges pour mettre en avant les nombreuses perspectives qui découlent de ces travaux, qui sont aussi bien sur le volet académique qu'industriel. Voilà, c'est une thèse très riche. Et pour toute cette raison, tous les membres du jury, à l'unanimité, vous décernent le grade de docteur et vous en félicitent. Bravo. Alors, le job n'est pas fini. Vous devez également prêter serment. Alors, je ne sais pas si vous le faites en français ou en anglais.
Oui, en français. Enfin, je l'ai imprimé en
non,
français.
très
Donc,
bien, parfait. Voilà, donc les reviewers sont arrivés.
Alors, en présence de mes pairs, parvenus à l'issue de mon doctorat en 2025 et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Oui, non, je voulais juste passer à quelques remerciements. So first, I would like to thank the jury for attending this defense. Thank for to the two reviewers, so Marius and Florian, for reading my manuscript and for all the questions that you had today. It was really nice to exchange about this topic with you. And so with Carola, I met the three of you during conferences this year, and it meant a lot to me to have your opinion on my work. And I'm really glad that you like it afterwards. Et sinon, je tiens à remercier aussi tous mes encadrants, du coup Gilles, Sandra qui sont là aujourd'hui, et aussi Margot et Claire. Merci pour tous vos conseils et votre soutien pendant ces années. Merci Ludovic d'être venu jusqu'ici pour présider ce jury. Merci à tous les collègues qui sont venus. Donc oui, vous êtes assez nombreux finalement pour être venus à ma soutenance. Merci aux amis, à ma belle famille, à ma famille qui sont venus un peu de toute la France jusqu'à Saclay. Puis finalement, merci à Elisa. Et grâce à qui je pense qu'il n'y aurait pas eu de pot après cette soutenance, auquel je vous invite maintenant. C'est dans la salle du foyer de l'auditorium. Voilà.
So, Marius, Florian, thank you so much. See you soon.
Thank you very much and congratulations. It was awesome work.
Voilà.
And yeah.
Thank you. Bye.
Congrats, Julie.
Thank you.
Congratulations, Julie. Very well done. Thank you. Really nice to you. It was really a pleasure.
Thank you very much. Yeah, I heard what you say at the beginning of the AutoML conference, and I was like, oh, there is an AutoML community in France. I was looking for it for so long, but I was really glad to
Well, now
see
we're
that
growing.
you exist.
Cool. This year is New York, so
This year, what?
the conference will be in New York.
Yeah,
so,
I know. I won't go there. I don't take the plane, but yeah, I know. Merci. Maintenant, c'est officiel. Ouais, ça marche pas. Je pense qu'il y a des gens qui seront contents de. Attends, j'en voulais juste le. Ouais.